purpose of this lab was to simulate the force of an induced magnetic field generated by a falling magnet and its effects on the magnet's free fall and compare it to observed data. And the application will be applying Faraday's law, Lenz's law, and the concept of magnetic flux. This is the link to my code. It's in the description of the video as well. Some of the fundamental formulas and concepts are the formula for the magnetic field of a dipole, Faraday's law, our EMF term for the change in flux of a magnet based on time, Lenz's law, which says that the force generated by the magnet is opposite to the change in flux. The force on the magnet generated by the induced current is opposite to the change in flux. And that the force on the magnet is equal to the current times the change in L cross the magnetic field. Here's the computational model. As discussed later, I'll go ahead and go over it now though. We can see the slope of velocity changing versus time. This first part up to, I guess, 0.1 seconds is where only gravity is affecting the magnet. And then right here is where the induced dipole is starting to push in the opposite direction of gravity against the magnet. And then the part where it's a flat line is where they're equal and the velocity is constant, and then the latter end of the graph is the magnet falling out of the end of the tube, where once again it's only gravity affecting its velocity. Some of the checkpoints and interpretation. So checkpoint 1, why could we not have used, say a steel tube? That's because compared to aluminum, steel is a ferrous metal and it has a magnetic field of its own, so that would have interfered with our experiment. Checkpoint 2. The magnet falls slower because the magnetic field induced from the current produced by the falling magnet applies a force in the opposite direction of gravity. Interpretation. If north is pointing down, the force on the magnet is upwards and it falls slower. That's because the induced current, if north is pointing down, is clockwise, which creates a force on the magnetic field, that points upward, which is against the direction of gravity. If south were pointed down, the opposite would happen, which would actually, the magnet would fall a little faster than it would if north were down. Therefore, red is north, and red is the clockwise current. 2. It would fall faster, as said above. The force would be in the same direction of gravity if south was pointing downwards. 3. The real measured time was less than our calculated time. This is because the tinfoil roll, for my instance, could have been thicker. There are absolutely interfering magnetic fields around me. My phone FPS is limited, and the instance where I could click the timer on and off, there may have been human error. I averaged some of it out, but it's still not perfect. And then one other thing we could have done is made in our program dy and dt smaller, so it could have done more calculations. So similar to if you're trying to approximate the area under a curve without doing an integral, the smaller sections you take, the closer you approach to the true value. So if we made those smaller, our error would have been less. And then, as discussed from the graph on the previous page, a negative slope means just gravity is affecting it. The positive slope means the magnetic force is equating to gravity and velocity is decreasing. Zero slope means magnetic force and gravitational force are equal, which equates to a constant v, or velocity. What if? If the resistance goes to 0, using our equation for current, where the limit of r approaches 0 is EMF over r. EMF would be a function of the magnetic field and velocity, and r would be our resistance. As that goes to 0, the current would approach infinity, which would equate to, as r gets closer to 0, the induced current increases, and the time for the magnet to fall to the tube will increase. That is, a slower descent as r gets smaller. With holes in the tube, the ability for a current to be induced would be lessened. This is because there are fewer continuous conductive ring segments. I have those in quotes. If you think about it as we did our calculation where it does pieces down the tube, I would consider each piece of size dy would be one continuous ring segment. Since there would be less of those, there's less places for the magnetic field to induce a current, and therefore a magnetic field on, which would allow for the free fall of the magnet to be faster. That's because the force on the magnet by the induced current would be overall less. So the time to fall would be smaller. Another way of thinking about it is from the concept of surface area in regard to flux. A lower magnetic flux means a lower induced current, and we reach the same conclusion we did above.